Hello and welcome to another orbital mechanics video from the book Orbital Mechanics for Engineering Students, and I am finally doing problem 2.47, and problem 2.47 is pretty cool. It says write a program like that, for example 2.18, to compute the trajectory of a spacecraft using the restricted three-body equations of motion. Use the program to design a trajectory from the Earth to the Earth-Moon Lagrange point L4, starting at 200 kilometers burn point. The path should take the coasting spacecraft to within 500 kilometers of L4 with a relative speed of not more than 1 kilometers per second. So what we have the Earth, we've got the Moon, and we've got the Lagrange points. It's like 3, 2, and 1. And we've got our spacecraft here. Yeah. And that's 200 kilometer radius from the center. And it needs to get here. This is L4. Hopefully you've watched my previous videos explaining the Lagrange points. If they were not clear, or you think I made a mistake on them, let me know and I'll try to improve on that. After a lot of thinking, I decided that the best way to get to L4 was via L3. So what I ended up doing was essentially going like this. Like that. And what I did initially is work out the energy at this point and the energy at this point to work out what change in velocity I would need to make to get to those points roughly. Now, remember, the Moon is orbiting the Earth, but this is worked out in the rotating frame. So everything is relative to the Moon and the Earth system. The Moon and the Earth don't change or move within this frame. They stay static. We're aligned to the axis at all times. So in order to get the energy at these points, we use the energy equation. Now, because there's two masses, so the energy equation is equal to our kinetic energy over 2 minus our gravitational potential energy. Now, the gravitational potential energy at this point will be the kinetic energy, which is speed, minus the potential energy of this and minus potential energy of that. So there's going to be mu1 and r1 minus mu2 and r2. Well, yeah, let's call that the distance from here to here and the distance from here to here, right? And it's going to be the same for L4, but in case of L4, these distances are all equal. It's an equilateral triangle, so it'd just be 2. It'll just be mu. So mu being both of them added together, it would be, so this is 3, and this is so mu equals mu1 plus mu2, right? And once you have the energy of those, you can take the energy that you start with, energy at 0, equals v squared over 2 minus mu 1 over r0. And so this will be your velocity initially, which you don't know what you want. You don't know what that will be. So, but you know what energy you want. So you want the energy of 3. So we simply make that equal to energy at 3. Don't need that. Bring that equation down here. And that is 3 minus mu1 over r1 minus mu2 over r2. And then solve for v squared here, v naught squared. Solve for v naught. And you get roughly like 10.9 or something, but you don't really need the exact answer. You just need a rough estimate. And all of these positions are essentially, on the outside of the on the orbit of the Moon is roughly 10.9. So that's the velocity you need to get in a direct transfer to the moon without any assists. So once you've figured that out, we can then go into MATLAB and we can start working out exactly where we want to be and how long it's going to take to get there, using just a bit of guesswork, really, and the advice from the book. So I'll switch over to MATLAB now. Thank you. So here we are in MATLAB. I have copied the function from example 2.18 to 2.47, and it has all the same parameters. You can read those through those. There have been the parameters that we've used throughout this series. And the main changes I've made is that I have 3 stages. So I have stage 1, stage 2, and Lagrange demo stage. So stage 1 is going from the Earth to Lagrange point 3, and stage 2 is going from Lagrange point 3 to Lagrange point 4, and then the Lagrange demo is just idling at Lagrange point 4 for 400 days, and you'll be able to see that works out quite nicely. In stage 1 we start at 200 kilometers. We have an angle of about 15 degrees to the horizontal. That's just above the horizontal, the y-axis, so the x-axis, sorry. And then our velocity is 10.9317 kilometers per second, and then our gamma, which is our flight angle against the horizon, is 27 degrees. And we're flying in the negative y direction in this one, so which we're in 2.18, the positive direction is up in the positive y direction. So I've changed it around a little bit to make it make sense for the direction we want to go. And then in stage 2 I've dropped to 2.1 kilometers per second, and phi is kept as what it was when we ended. So the only thing we change between the stages is the speed, and that's along the axis of movement. So I'm not rotating the spacecraft in order to fix the angle or anything like that. It's just speeding up and slowing down along its velocity vector. So I'm just going to run it, and you can see the results. So here we have the Earth, the Moon is over here, and we start off, you can see, about 15 degrees above the horizontal, and then about 27 degrees flight angle down here. And off it goes around to the Lagrange point 3. So there we can see we end roughly around there. So I've just roughly around the horizontal to land on the Lagrange point 3. And then from Lagrange point 3, at Lagrange point 3 we're running at about 1.2 kilometers per second, so I have to speed up to 2 kilometers per second to circularize the orbit a little bit, and that will get us into a nice spot here, which is the equilateral triangle, Lagrange point 4. Zoom in closer, you can see for 400 days it is in a stable orbit in the Lagrange point. I can actually mess around with it a little bit if I move if I just take a little bit longer to get there. For instance, if I coast for a little bit longer before dropping, you can actually see it will actually get a little bit bigger eventually. Oh, it's a little bit smaller. Once I come out, see it's bigger now, right? So we've got quite a bit of flexibility because of the angle that I'm coming in at, and the speed that I'm at is nice. So I've made it a lot bigger now. I'm definitely within the requirements of the question. I'm actually well within tolerance. I'm at 0.005 kilometers per second relative speed. So yeah, I'm pretty close to the. I think it wanted me to be within 500 kilometers. I think it was asking for. Yeah, I'm well within that. So yeah, and I mean I tried getting from the from the Earth up to the Lagrange point, just going direct. It's just really difficult to kind of land on it, just point in the direction of it and go, and it was very difficult to accurately land on the spot that was at the Lagrange point. I might be better at it now. Playing with the values can be quite fiddly, but I really only decided to make progress when I went to Lagrange point 3, and once I got to 3, the rest just sort of sorted itself out, because I'm coming around in the orbit of the moon anyway, so it just worked out. If I was going to Lagrange point 5, which is down here, I'd go the other way, but that would actually be going in the orbit of the moon, counterclockwise, so that would be different. It'd be a different amount of speed, so I might try that as well. Yeah, if you have any questions or you think I've made a mistake, leave it down in the comments below. The MATLAB will be in the description. I'll be on to chapter 3, so next video. Thank you very much. Goodbye.